welcome to a session of US-based webinar series. Uh, Today we have a topic on GPS. We are very glad to have three eminent panelists and a chief speaker. He's Dr. M.R. Sivaraman sir. He is one of the great scientists of ISRO. Uh, uh, you and the three panelists is also in ISRO, and we are very happy to have them in our webinar series. And I hope all of you will enjoy. And first of all, I just want to thank you for all participants for making our the last 9 webinars as a successful mission. And we hope and that you will make it this webinar also a successful one. And Shajisa will introduce the our panelists and the speaker. And over to Shajisa for that.
Okay, sir. Thank you, Varun. We are on the 10th webinar in this day. We are proudly sitting here with the 10th one, and we started this journey on the 23rd of May. And we are so happy to introduce a lot of eminent scientists of India, especially in the field of space and in connection with the ISRO here. And normally the common people are thinking there is an ISRO, what they are doing, they are sending some rockets and spending some monies there. And whenever we say about the ISRO, we know there is an office at Bangalore and somewhere else. That's the thing. Then comes an idea in our mind, what else this ISRO, what is the benefit of this ISRO to the common man? How it is being used here? Then that question reached to for that answer, we reached the special institution that is SAC, Space Application Center, Ahmedabad. Today, we have four eminent scientists from ISRO. Two of them are veterans and two of them are still working energetically for the success of this ISRO, great organization of India. And in this webinar, the presenter is the veteran ISRO scientist, senior scientist, Dr. M.R. Sivaraman sir. He joined in ISRO in 1966, and he was part of the several strategic functions of ISRO, and he was part of development of geo receivers and its applications, and development of GPS receivers and its applications, satellite navigation system programs like Gagan and IRNSS, and development of time synchronization techniques, and development of ionospheric and tropospheric models of Gagan. And all these are the contribution to these wonderful organizations. And we are lucky to get this kind of a veteran person who are well versed with this navigation, and we are without resorting to the techniques of USA. We developed our own navigation and satellite techniques for these things and remote sensing. And we make a warm welcome to the veteran scientists to our group, UL Space Club. Welcome, M.R. Sivaraman sir. And we are proudly presenting one more scientist here. He was a mission director of ISRO. Sri Sundaramurthy sir, Dr. Sundaramurthy sir, he was the mission director for Indian Communication and Meteorological Service System, and he took part different major functions of India. Especially, it was Eutelsat. It was a satellite for the meteorological development of India, and he was part of ISRO Andrix and several other milestone activities of ISRO. We are proudly and with humble, and we are welcoming our our panelist, Dr. Sundaramurthy sir, to this occasion. Along with these two veteran scientists, we have two energetic personalities. One is Dr. Rajat Ajaria, scientist and course director of SSC ISRO Ahmedabad, and is very interested in joining this webinar and in nurturing these students for their future success. Along with him, his friend and colleague, Dr. Ashish Kumar Shukla, is also a scientist from SAC ISRO Ahmedabad, is joining here and nourish our children to the high altitude of space. And we warm welcome these two scientists, energetic scientists of India, ISRO, Dr. Rajat Ajaria and Dr. Ashish Kumar Shukla, to this webinar. And along with that, we have a lot of eminent personalities from different parts of India, especially who are related to the ISRO and some other organization. Along with them, we have the continuous batch of our webinar family. And the aim of this webinar is to develop or create an environment, educational environment to our students to achieve their goals. That the target group is US Space Club members and some group students of all over the Kerala, and there may be some few people from outside Kerala. A warm welcome to all, and I proudly invite Dr. M.R. Sivaraman sir for his presentation. Welcome, sir.
Thank you very much, Mr. Sajil. Good afternoon all. Welcome to my lecture. Now, today's talk is on global positioning system, that is GPS. That is well known to all of you. And I will explain in very simple terms what is GPS and how it works and our competitor NAVIC. Next one. Before understanding GPS, you should know what is meant by geodesy and meant by positioning. GPS essentially is a satellite system that gives position location. That is, if you have got addresses of your house, you are able to easily locate your house in a map. And if you are able to stick a pin on a globe where your house is located, you can easily locate it on even a globe or a map or other things that will be shown in the next slides. Instead of getting addresses where you will be able to relocate you, an alternative system is to define a spatial reference system. That is a Cartesian coordinate system XYZ or polar coordinate system phi lambda h that we have studied in our school and colleges. This will be also, if you know these, either Cartesian or polar coordinates, you can relocate your position on the globe of the Earth or any map also. These coordinates are essentially used in GPS to define and locate your position on a map that can provide many location-based services. Popular location-based services are Ola and Uber. You may be using that and you know how it works. This is because the coordinates are available. Locating different buildings in a campus, building roads and bridges, conducting and land service, and making maps and promote other important applications. Next one. Next one. This is a globe, and I show you a position of location. Once you know the coordinates of Ahmedabad, latitude, longitude, right, you know where you can locate it. You can put a pin and locate the position. Next one. Next. This is a map of Gujarat. And again, once you know the coordinates, you can locate Ahmedabad on that. Next one. This is a map of Ahmedabad, very detailed map. The famous place called Law Garden. And if I am sitting there and I know my coordinates, I can sit, I know where I am sitting there. So the coordinates are very important. Next one. Next one, please. Yes, this is the map of our famous CG road in Ahmedabad. This is a satellite map, and you see here there are different locations located here, like Baikaka Hall and so many other things. These are all possible because you know the coordinates, and you can relocate them once you know the coordinates. And this is the famous Google Map way of tracking yourself. Next. Now, before understanding GPS, one more thing you should know is what is the coordinate system used? The topographical surface of the Earth, that is the physical surface of the Earth, is the actual surface of the Earth. But it is very irregular. The physical surface is not regular. And it is difficult to define any coordinate system on this irregular physical surface. An early mathematical surface that fits physical surface of the Earth both in land and sea is called what is called geode or mean sea level. And even this mean sea level is irregular and it is not used in coordinates, depending coordinates. Mean sea level, that is geode, is an undisturbed sea surface level in land in equilibrium between effect of Earth attraction and centrifugal force of the Earth rotation if canals were dug into land to allow ocean to enter the world. In fact, all over surveyors in the map, the height of any places is with respect to geode. But using GPS, you can have another system by which the height is defined in a different way. But because the geode also, like the physical surface, is irregular and cannot be used to have a suitable coordinate system. Next one.
Excuse me, Sivaraman sir, can I please interfere for a moment?
Hello?
Sivaraman sir, can I please interfere for a moment? Shadil sir, please take care. There's a bit of sound coming out from the background.
Yes.
Everybody, please kindly mute yourself. We need the proper working of the webinar, so please kindly mute.
Okay, sir. Continue, sir. Please.
Now, this is the diagram showing the size and shape of the Earth. It is the red one, is the geode. The irregular surface, most irregular surface is the surface of the Earth, that is the physical surface. And the green one is the ellipsoid. Next one. I will now define what is meant by ellipsoid. All the coordinate systems in GPS are determined with respect to this ellipsoid. Next slide, please. The best smooth surface that can be used to define a coordinate system is an ellipsoid, or it is also called spheroid sometimes. It is a three-dimensional shape formed by rotating an ellipse either around its major axis or around minor axis. That shape can be modeled by an ellipsoid formed by rotating an ellipse around the minor axis. So this is the best surface that fits the physical surface of the Earth. So it is chosen for defining a coordinate system. It is described by two numbers, semi-major axis A or a semi-major axis B, or semi-major axis A or the flattening F, or semi-major axis A and eccentricity E. Next. This is the shape of the ellipsoid. You can see here A, that is a semi-major axis, and B, that is a semi-major axis, and N is the north towards the direction of axis of rotation of the Earth. So this is the best fitting surface to the physical surface of the Earth, and this is used. The center of this ellipsoid coincides with the center of the Earth. Next. Now, this is another diagram showing the irregular Earth surface where the mountain is there and ocean is there. Then the geode undulation and also the ellipsoid. This is a better diagram showing geode, ellipsoid, and physical surface. Next one. Now, to represent any point on the physical surface of the Earth, you also need a suitable coordinate system. The coordinate system used in GPS is Earth-centered, Earth-fixed coordinate system. That is, the Earth is assumed not rotating, and the center of the coordinate system is the center of the Earth. It is most popularly used and is also sometimes known as conventional terrestrial system. In the figure next, I will show you the coordinate system. Here, the physical surface of the Earth is simplified by an ellipsoid. The origin of the coordinate system is taken to the center of the Earth, which is also the center of the ellipsoid. The position of a location P on the physical surface is represented by X, Y, Z. That is shown in the next view graph. Next one, please. See here, you have got point P, that is the point where you are located, anywhere on the Earth. And you can see the ellipsoid, that is the ellipsoid, and you are above the ellipsoid at a particular height H. That is normal drawn from P will be going down, and the height is defined as H above with respect to this normal. Now, you have got the x-axis that is passing through the Greenwich meridian, and y-axis 90-degree perpendicular to that, and z-axis along the axis of the Earth. In this coordinate system, you can define a coordinate x, y, and z in Cartesian, or phi, lambda, and h. So x, y, z are the Cartesian coordinate system, and phi, lambda, h is a polar coordinate system. The aim of GPS is to determine these to as much accuracy as possible. So that is what GPS does. Now, how it does, I will be telling now. Next. Next, please. Now, geodetic latitude, the angle which is normal to the ellipsoid at a station makes with the plane of the geodetic equator. In recording a geodetic position, it is essential that ellipsoid it is base is also stated. Whichever ellipsoid you use, you should also state that. The longitude is the angle between the plane of the geodetic meridian at a station and the plane of the geodetic meridian at Greenwich. The geodetic coordinates are used for mapping. And h is the height between the ellipsoid and the physical surface on which you are. Next. Now, in GPS, there are some constants which are used universally. That use these constants only when you use a GPS measurement and try to calculate this. These are basically the ellipsoid parameters, semi-major axis and flattening. The values are given here. Earth's angular velocity is this, whatever is given here. Earth's gravitational constant and speed of light in vacuum. These are all fixed, and these have to be used whenever you have to solve GPS equation to get your coordinates. Next. This is called World Geodetic System. Global Positioning System, or GPS, is the first satellite navigation system based on the principle of what is called one-way ranging put into operation. That is, here, only the satellite will be transmitting the signal to the Earth, and the receiver will receive that and determine the distance to the satellite. It is only one way. So that is called one-way ranging. There are other similar systems developed, like GLONASS, Global Navigation Satellite System of Russia, Galileo by European Union, BIDO by China, NAVI by India. All these four are partially operational and under testing. Basically, a satellite navigation system consists of three segments: a space segment, control segment, and a user segment. I will explain what are these segments in GPS. Next. Now, this diagram basically shows the three segments. You have got the space segment where there are minimum 4 satellites are required. See, 4 are shown. These will be transmitting some signal to the user. Before that, these satellites will be tracked by a ground station that is called monitoring station. They will be receiving some ranging signal from the satellites, and using the ranging signal, it will be sent to a master control station. The following parameters will be determined, like the satellite ephemeris or the 6 Keplerian parameter under perturbation, clock correction, because the satellites atomic clock, they have to be corrected quite often, and the correction parameter, atmospheric data that is used for doing what ionospheric and tropospheric correction, which I will come detail later, and almanac, that is the approximate position of all other satellites. These satellites transmit to the user coded ranging signal. What is coded ranging signal? I will come later. Then atmospheric data and almanac and their position also. To get your position of an aircraft or anything, you should know the position of satellites also. They are transmitted by the Keplerian parameter by the satellites. So using this information, the user segment will determine its position. This is basically a satellite system. Next. Now this is the GPS block 2A satellite. Now there are satellite that is block 3, where the satellite is much better and the clocks are still better, and it determines its own position and also transmits. So you need not do an uploading from ground station to transmit their position. Next. The GPS space segment consists of 24 satellites. Total 24. They are in 6 different orbital planes. The 6 orbital planes are equispaced with 60 degrees apart, and each plane contains 4 satellites each. There are 6 different planes, 6 into 60 is 360 degree, and each plane contains 4 satellites. These satellites have a period of 12 hours radial time and a semi-major axis of 29,561.75 kilometers. The eccentricity of the orbit is nearly zero, generally less than 0.02, and inclination or orbital plane is 50. The satellite constellation allows 4 satellites to be visible to user anywhere, anytime. That's the basic by 24 satellites were launched. The 4 satellites in each orbit plane are unevenly spaced, so as to minimize what is called satellite outage. These are the space segment. There are 6 orbital planes, 55-degree inclined, and each orbital planes contains 4 satellites each, total 24 satellites. Next. All the satellites carry basically a payload. The heart of the satellite is an atomic clock, which has got a stability of 10 to the power 13 minus 12. That is in 10 to the power minus 12, 10 to the power 13 seconds, the clock will drift 1 second only. That is 10 to the power minus 13 is a stability. It can be ended as CCM beam or BM beam, but nowadays, even the maser clocks are available. European Union has tried the maser clocks, which are still better, 10 to the power minus 15. That is in 10 to the power 15 seconds, the clock will drift by 1 second. It has got a basic memory because it has to store the orbital parameters, transmit them from the ground and retransmit. It has got a receiver to receive messages from the ground to put it into the memory, and a transmitter that will transmit a ranging signal and the parameters. GPS satellite transmits 2 frequencies, that is 1575.42 and 1227.6 megahertz. These are known as L1 and L2. On that, there are 2 PRN codes. I will come to that later. 1.023 megahertz or 10.3 megahertz. They are basically called ranging signal, and also the navigation data, that is the ephemeris and other parameters, at the rate of 50 hertz. These 2 information is transmitted at 2 frequencies. The L1 signal is biphase modulated by a 10.23 megahertz precision PR code, P code, and a 1.023 megahertz CA code. Now I will come to that CA code and P code later. Next. The space segment consists of at least 4 satellites. That is, minimum you need 4 satellites to get your position. They should be visible to navigate at any time. Typically, these satellites are in near circular orbits 20,000 kilometers above the Earth. That is what the GPS does. This I have repeated again. A PRN code is a. Now I will come into the PRN code. That is the CA code and P code, what I said. 10.23 megahertz P code and 1.023 megahertz code. It is called pseudo-random noise code, PRN code. It is a unique binary sequence. Just if you have got a torch, you put on the torch and put it off at regular intervals. When it is on, you consider it as 1, and when it is off, it is like 0. Similarly, that satellite generates a plus 5 volt and 0 volt signal at the rate of 1 megahertz or 10 megahertz. They are called zeros and ones, and this is called pseudo-random noise. It has the appearance of having been chosen on the basis of repeated coin losses. It is very random. It looks random, but it is pseudo-random. If you know the a priori information, you can detect this code. It looks random, but with a priori information, the sequence of bits, which repeats for short time of 1 millisecond, it is only partially random, and the name pseudo-random noise, and each satellite is assigned different PRN code. So each satellite has got its own code. Next. This is a PR code, example of a PRN code. See, when the pulse is up, it is called 1. When it is down, it is 0. So it is 0, 1, 0, 1, 1, 1, 1, 0, 0, like that. You see here, the bits of ones and zeros, plus 5 volt and 0 volt. But if you see after some time, at a particular place, see it is repeating. Again, the pattern repeats. Somewhere in the center, you will see, again it is repeating 1, 0, 1, 0, 0, like that. So it is sequence. But if you see at any time receives the signal, and if you don't know the start of the signal, you cannot detect what is the code that is transmitted. So that is why it is called PRN code. Next. GPS transmits 2 codes, a course acquisition code and a precision code. Course acquisition code, because it is called it gives approximate range to satellite, and P code is a called precise code that gives better accuracy of ranging to the signal, that is distance to satellite. Ranging means distance to satellite. The CA code is meant for civilian users. It is not given to defense outsiders. It is meant for only for US and its alloys. It is relatively short code with a duration a period of 2 to the power 10 minus 1, that is 1023 bits repeats every 1 millisecond at a rate of 1.023 megahertz. The P code is a long code with a clock rate of 10.23 megahertz and a period of 1 week. Next. This is the P code is not given to the civilians, but still some receivers are available using the P code for geodetic code. Next. Next one. So this table summarizes the signal structure. Two signals, L1 and L2, 1575.42 into 10 to the power 6 megahertz and 1227.6 into 10 to the power 8, 10 to the power 6. So you see, when you want to send any information which is a lower bit, like the navigation data, which is at 50 hertz per second, you need a higher frequency carrier. So this is called carrier frequency. This high frequency signal carries the navigation message. They are modulated on that, and that is how the user gets navigation data. And PRN code also, which is 10.23 megahertz, lower than the transmitter frequency, modulate that, and that is received by the user. Just like in your TV, your video and audio are transmitted very high frequency. Both the video and audio are lower frequency signal. They modulate the signal and transmitter. Your TV receives that, demodulates, and gets the signal. These are the power given. The transmitter power is what is called dBW. You can read and find out what is dBW. It is a decibel scale. The C power is minus 160 to minus 163 for L1 and minus 166 for L2. These signals are below the noise level. That is a background radio noise. And that is the beauty of that. If you don't know which satellite is at what place, it is difficult to recover the signal from the noise. But there is a technique called CDMA technique, by which you can generate the replica of the code and match it with the received signal and recover the signal. That is, it is a deeper, you need not go into that. Next. Next slide. So basically the signal is under noise and very difficult to detect it unless you know the code a priori. Now coming to the second one, that is the GPS control segment. Basically, the control station are a worldwide tracking stations that take the GPS signals, receive the ranging signal and navigation data, and the data is sent to a master station for determining the orbital parameters. Now, once it is determined, the data is sent to a control station and retransmit to the satellite, stored in the satellite, and they transmit the signal for the next data for the next 12 hours. So once in 12 hours, this data uplink takes place. Next one. These are the stations, worldwide stations set up by US Department of Defense. Basically, GPS is a US Department of Defense system. So these are all the tracking stations worldwide. So anytime any one of the stations will be seeing any one of the 24 satellites, getting the tracking data, the whole tracking data will go to a center station where they will process the data and determine the ephemeris of the satellite. That is the position of the satellites. Next. So this is basically the function of control segment. So basically, control segment track all visible GPS satellites and sends the tracking data in real time to a master station in Colorado. The tracking data means ranging station, distance to the satellite measurement. The master station computes the future orbital parameters. There are basically 6 orbital parameters, Keplerian parameters, and also their perturbations for the next 12 hours and satellite clock corrections also. This is stored and transmitted on the respective satellites to store them on the satellite or in the onboard memory and whenever they pass over the master station, it is retransmitted by the satellites along with PRN code to the user as described above. Next. In short, the main functions of control segment are monitor satellite orbits, monitor satellite health, maintain GPS time, predict ephemeris and clock parameters, update navigation messages, command satellites maneuvers. The ground stations are all in well surveyed points, and that is how the orbit determination is done. Next. These are all the basic navigation data, which I already told you. Next. The GPS receiver nowadays is available in the form of chip. Basically, it contains an active antenna, an RF IF front end, and a digital signal processor. At the end of the digital signal processor, you will get the position where you are doing. See, these kind of very small chips are sitting in your mobile, like your Apple iPhone. There is a GPS chip sitting, and that is how you are able to see where you are located. So these are very small chips integrated using integrated circuits, and this is basically the contains an active antenna, RFIF front end, and digital signal processor. So this is basically a GPS receiver. Next. Now coming to the principle of ranging. The basic principle of GPS is what is called trilateration or triangulation. Now suppose you have got three satellites, and their positions are very well known with respect to ellipsoid. Their X, Y, Z coordinates are very well known, all the three. Now suppose you measure the distance to satellite 1, that is the left one. You measure the distance as shown by the line joining the satellite down. At that distance, you can draw a sphere. So when the satellite distance is determined, anywhere on that sphere, part of the sphere which I have shown, the user is lying. Now you take the second one, which is on the right side of that. You measure the distance to that satellite as accurately as possible. You get a second sphere, and it will intersect to the first sphere. Now you have got a third satellite. You measure the distance to a satellite, and you will get third sphere, and the three spheres will intersect at a point. And that is how the position is determined. This can be put in equation form. I will show you that later. So this is basically a principle of triangulation or trilateration. Next. So basically the equations are R1, R2, R3. Suppose your satellites are XU by U, XU1 by U1, ZU1 is a satellite 1, and XU by U, ZU are user position. R1 is square root of XU1 minus XU whole square plus YU1 minus YU whole square plus ZU1 minus ZU whole square. So you have got three equations similar to that from three satellites. They are under square root, and it is non-linear. It has to be linear, right? And you can solve for XU by U, ZU. Once you know X1 by U1, Z1, X2 by 2, Z2, and X3 by 3, Z3. This is the equation to be solved. Take it your position once you know the satellite position. Next. How the user segment measures the distance. The user receiver generates a replica of the PRN code. See, the user knows a priori which satellite is above our horizon. Say satellite number 1, 2, 3, 4. In each one of them has got a priori known PRN code, assigned PRN code. So the receiver knows that these satellites are transmitting the PRN codes which is known to you. So the user receiver, what it does is, it generates one of the PRN codes. That is a replica of the PRN code what the satellite is transmitting. Now this PRN code is synchronized to your local clock, where the PRN code by satellite is synchronized to atomic clock. So it is offset with respect to the satellite atomic clock by a time delta t. Your clock is offset. So there is an error of delta t. Now what it does is the user receiver slides the locally generated, the PRN code generated from satellite will be reaching the ground with a time delay delta t. So it will be ahead of the locally generated code, which is exactly synchronized. You have to side the local code, match it with the received code, and when the matching takes place, the correlation is maximum, and how much you have delayed the signal multiplied by velocity light will give the distance to the satellite. That is, you have to assume that the radio wave travels with the velocity light, which is not true to the presence of ionosphere and troposphere. but there you can correct for that because atmospheric data is transmitted. Now, if you have got 4 satellites transmitting different PRN codes, you can determine all the 4 ranges simultaneously, R1 dash, R2 dash, R3, R3 dash, and R4 dash. Next. Now, this is the previous. This is a topmost diagram, topmost one. There are 4 satellites. Below that, I have shown you a pulse. So this is a pulse, simultaneous pulse with a different code inside from the 4 satellites. Each one of them will be reaching the receiver at 4 different times. So the one of the whatever code you have generated, shifted and matched with the receiver code, and the time delay is measured. And this time delay multiplied by velocity delay will give the distance. Since there are 4 different codes, each code you can match by generating each code separately, and all the 4 distances can be determined. This is basically the principle of ranging. Next. Next. This is another diagram showing the principle of ranging. The satellite generates a PRN code. It is received with a delay. You see it repeats after a time delay. The receiver also generates, but that is shifted and then matched with the transmitted one received from the satellite, and the time delay is measured and it is multiplied by velocity delay. In actual practice, what is done is, each pulse leaving exactly what time it has left the satellite. And when you generate on the ground, it will come with a time delay delta t. And you can measure with your local clock at what time it is received on the ground. So that way also you can measure the time delay, and that is the best way to determine the time delay and get the range. Next. Next one. So this is a diagram showing the shift, the received signal, and time delay, time difference. Next. Since 4 satellites transmit different PRN code, you can get 4 ranges: R1 dash, R2 dash, R3 dash, R4 dash. All the 4 satellites carry, all the 4 satellite clock and receiver clocks are offset with respect to a standard time difference. So that time, that offset has to be known. The satellite clock offsets are known by the control station, and they are transmitted, the corrections are applied. Corrections are transmitted to the users. In addition, there is a propagation delay also due to what is called ionosphere and troposphere. So it is not the true range that you are measuring, it is corrupted range, and that is why it is called a pseudo range, approximate range. Next. Next. Yeah, previous one. This shows how accurately you can determine range to the satellite. Each code, a 1.033 megahertz, is a 1 microsecond each. When you match the transmitter code with the local code, you can measure a time delay with accuracy of 1/10 of 1 microsecond. That is 100 nanosecond. So that is 100 into 10 to the power minus 7 second. That is multiplied by velocity light 3 into 10 to the power 8. Accuracy 30 meters. That is, the CA code gives an accuracy of measurement to the distance 30 meters. The distances can vary from 20,000 to 24,000 kilometers, and that is measured in accuracy of 30 meters. If you receive P code, which is 10 times faster, the accuracy is 3 meters. Next. So this is typical signal how it reaches. There are so many errors: orbital error, clock error, ionospheric refraction error, tropospheric refraction error. These are all to be applied using different modes, and after that, the real corrected range you will get. These are the major sources of errors in GPS or Navi. Next. Now you see the 4 satellites, and their positions are well known. Now R1, R2, R3, R4 are the real range, exact range. There are errors due to satellite clock C times delta TS, then due to receiver clock C times delta TU, and also atmospheric delay C times delta TA. So the real range what you measure is next one. is Ri dash. Actually, you want to measure the Ri, that is the exact distance with no error. But there is a clock error, atmospheric delay error, and also the satellite clock error. So the equation becomes Ri dash, that is a pseudo range, is Ri, that is the exact geometric range, plus C times delta Tu, that is a receiver clock error contribution to the error, then C times delta TAA, atmospheric delay, and C times delta TSI, that is satellite clock error. So major errors are atmospheric delay, user clock delay, and atmospheric clock delay, satellite clock delay. The satellite clock delay can be corrected for because it satellite transmits the correction, how much you have to correct to get a real time. Delta TA can be corrected for using atmospheric model for ionosphere and troposphere. And these models are also parameters are transmitted by the satellite. And delta TU is just receiver clock error, receiver clock offset with respect to the satellite clock, which is an unknown. Now you see Ri is a function of x, y, z, and you have got a fourth unknown, that is delta Tu. You don't know how accurate is your local clock. That is delta Tu, local clock offset. That has to be determined. So you have got four unknowns, x, y, z, and delta Tu. So to solve four unknowns, you need a four equations, four simultaneous equations. That is why minimum four satellites are required to solve to get your position. Otherwise, only three satellites are enough, as I had shown in the previous diagram of triangulation. Next one. So this is a basic equation. You see, this diagram shows if you know the range to one satellite, it will be user will be lying somewhere on a sphere. Next one. Next, if you have got two satellites, previous one, you will see the two spheres, that is the distance to satellite, will intersect in a circle. Next, if we have got measurement from three satellites, the measurement from three satellites will intersect at 2 points. One will be on the surface of the Earth, other will be outside. So you know where the position on the Earth. But these measurements are not exact. There is an error in that sphere, the measurements of sphere, and they have to be corrected for. And one of the error is the receiver clock offset with respect to atomic clock. So that is solved for. So x, y, z, and delta T is solved. So, but this is a basic principle geometrically shown, intersection of three spheres. Give the position. Next. This is another diagram showing two spheres, three spheres, and then four spheres. Next. Now, in addition to the errors due to atmosphere, that is the residual errors due to atmosphere, there are the position accuracy depends on the accuracy of the position of the satellites also. If you have got four satellites as shown in the left side, they are quite wide apart. There is a parameter called geometric dilution of position. That is, the parameter is very good. It is very low. The error in positioning is given by geometric dilution of position GDOP multiplied by user equivalent range error. That is the total error in the range. If the GDOP is small and also user equivalent range error is also small, you will get a better position. So one way to improve is you select four satellites which are wide apart. If you select four satellites which are close by, in determining your positions, you will be having more error. Next. Now this table shows the various error terms. I think you can read it in relation. Satellite clock stability. There was an error called selective availability. Yes, purposely used to dither the signal transmission so that the user will have error, and only then US defense and their allies will know how much they are doing that dithering. So now it is removed because US want that their receiver to be used in aircraft, that is civilians. So now that error is not there. The control segment error is ephemeris error. How accurately you can determine the position of satellite? That is around 4.5 meter for CA and P code. In ionospheric delay, 25 meter residual error, after correction. In P code, it's a dual frequency transmission used. So the accuracy is better 2 meter. Tropospheric delay of the order 3 meter. multipath, that is, you may receive instead of direct reflection from the hill, then the receiver noise, some of the square root of some of the errors, some of the square root of the errors is what is called user equivalent range error, and you have got horizontal accuracy of the order of 50 to 60 meter and vertical accuracy of 105 meter if you use CA code, and if you use P code, it is slightly better, 22 and 30 meter. Actually, the P code gives better accuracy, and that is why US never wants others to use that. In fact, during Iraq war, they did not allow people to use P code. Next. Now, this is basically the principle of NAVIC, principle of GPS. Now, in ISRO, we also developed a system that is competing with GPS. Now, that is called NAVIC. It is first started as IRNSS, that is Indian Regional Navigation Satellite System. NAVIC is an operational name for IRNSS, the Indian Regional Navigation Satellite System. It stands for Indian Regional Navigation Satellite System. It is a short word for also for navigation using Indian constellation. So NAVIC, NAVIC. It was named NAVIC. NAVIC means sailor or navigator or a boatman in Sanskrit and Hindi and many other Indian languages too. So our naming IRNS as NAVIC is suitable, is very appropriate. It is an independent regional navigation satellite system. That is, this system provides service only over Indian region, and it has been developed by Indian ISRO, and will provide position services in land, air, and sea, including what is called location-based services over an area within Indian subcontinent plus around 1,500 meters beyond Indian subcontinent. The principle is very similar to GPS of the Department of Defense, and it can be also called, we call it a Deshi GPS. Next. Apart from GPS, Russia has global navigation satellite system, GLONASS. European countries are developing Galileo. China is developing BIDO. Japan is developing QZSS, causes in its satellite system, all very similar to GPS. Why we developed NAVIC? NAVIC was developed by ISRO because access to foreign government-controlled global navigation satellite system, any other that is mentioned above, is not guaranteed in hostile situations, as happened to the Indian military in 1999 when it was dependent on the American global positioning system during the Kargil war. So the Indian government approved IRNSS project in May 2006. Now the system is operational and over our Indian subcontinent. Now you see, unlike GPS and other systems, ISRO does not have fund to launch 24 satellites or more, so that anytime over India we can get 4 satellites. So what we thought that we will have minimum 7 satellites going all over the earth, all over Indian region only, and these 7 satellites will provide service only over our own country. That is good enough. We should protect ourselves. Why we should bother about other part of the world and give service? So that is what the basic difference between GPS and NAVIC. NAVIC has got only 7 satellites. GPS and other system have 24 and more than that. So it has got basically 7 satellites. 4 of them are in geosynchronous satellites and 3 of them in geostationary orbit. There's a ground station, and it is the signal is received from the 7 satellites. The received data is used to get the orbital parameters. Then it is uplinked to satellite. Satellite returns to the aircraft, and it gets the position. Next. Next one. The space segment consists of previous. The space segment consists of 7 satellites. 3 are in geostationary satellites located at 34 degree, 83 degree, and 132 degree. They are inclined at 29 degrees to geosynchronous, inclined 29 degree, and geosynchronous satellites at 55 and 111 degree east. They are in pair of that. Like GPS, it carries an atomic clock, The transmitters are S-band and L-band. Memory to store navigation data, which is computed from IR master control station, and the PR and code generators. The satellite generates PR and code well synchronized to atomic clock on board to an accuracy better than 100 nanosecond. And like GPS, navigation data along with PR and code will be modulated on S and L band, transmitted to the user, and the user will get to the position. All the 7 satellites are visible continuously over the engine region. Next. These are the 7 satellites launched, 1B, 1C, 1D, 1E, 1F, 1G. 2 satellites fail, 1A and 1H. Next. So minimum 7 are kept always. So these are the 7 satellites. Next. They are all our engine region. This is the satellite. Next. These are the services provided. One is called Standard Positioning Services, SPS. Other is the Restricted Positioning Services used for only by defense. The 2 frequencies are L5 and S-band. This is the signal coverage. This much signal coverage is done. So even beyond India, the service is available. Next. The control segment consists of a network of ranging stations, the master control station, telemetry and command station. So they track the satellites, that is the range, determine the orbital parameters and transmit to satellites. Satellite retransmits. Next. I will show you the diagram of the 15 ranging stations. Next. These are the stations which are used as ranging stations. That is, apart from using the satellite transmitter L and S band, they have got a transmission at a C cross C band. That is basically the ranging station, ranging which is data which is used for getting the position of the satellite. Next. User receiver contains a small handheld receiver with a small antenna. User receiver, in addition to antenna, has a crystal clock, RF segment, digital segment, and a small computer like GPS. It receives signal from all the visible satellites, minimum 4 at a time, determines what is called pseudo range, approximate range to all satellites, recovers navigation data. It then calculates XYZ and XYZ or pi lambda h, either Cartesian or polar coordinates. In addition, user receiver computes the clock offset from the satellite clock to an accuracy of 100 nanosecond. The information is passed on to a computer for computing the position. Next. These are the different types of navigation receiver developed by Space Application Center, in which Dr. Rajat and Dr. Ashish has taken part. There's a big team, and even there's a separate group working on this. You can see the antenna in the left-hand corner side, tabletop model, another model, and there is receiver. There is a navigation messaging receiver. There's a new one. That is, when the satellite transmits messages, there are some blank space, where you can transmit message to fishermen also. So additional messages like in fishermen. In Kerala, this is provided to fishermen, Navic receivers. They know their position, and also any information about the weather and everything are also transmitted, so they can come back easily. So there is a messaging system also available. Advance warning can be given. The one lowermost is a chip that can go into your handheld mobile. That has also been developed, and the technology has been handed over to different industries, and they are developing it. Next. This is the error budget. You can go through later. We get an accuracy of less than 18 meter. Actually, the accuracy obtained is better than that, better than 5 meter. Dr. Shukla will be able to answer that better. Next. The major features are the service is available continuously, 24/7. It is independent of any foreign navigation satellite. It is sufficient in good accuracy for many applications. If you get 5 meter accuracy or even 20 meter accuracy, it is good. 20 meter is 1/4 of 1/5 of a football ground. It is available in all weather, rain and everything. Low cost receivers are available. It is in the form of a chip, which can go into your mobiles. Receivers are available in small integrated chips. Receivers are automatic. and no user skill or special training is required. Receiver can be easily integrated with mobile phones or easily with laptop PCs. Provides an alert on that satellite failure and wrong position. This is one of the advantages. Our NAVIC has got a monitoring system by which if one of the satellite fails or transmit wrong data, we can alert. This doesn't exist in GPS. You have to independently do it, otherwise it will give wrong information. Next. Now we'll shortly spend another 5 minutes. These are all the various applications, terrestrial, air, and marine navigation. That is, you can use it to get your position either on the ground or an aircraft in the air, or even rockets or missiles, and marine navigation like ships or even submarines. So this is one of the biggest applications. It is used in remote sensing. I will come to this later. Geodesy and mapping, location-based services. That is, your Ola and Uber are depending on this. Geographical information system. I will come to that later. Information technology, ionospheric studies. You can get the total electron content and get also syndication parameter. You can get you can use it for satellite meteorology. You can get a total water vapor content and temperature. Precise time and time measurement, satellite orbit determination, and launch vehicle tracking. This is one of the applications ISRO is using. We use these receivers in the satellite and in the launch vehicle to get their position. Integration with mobile phones for common man, detecting landslides and tectonic movements, and even you can detect tectonic movements, disaster management, vehicle tracking and fleet management, terrestrial navigation like anchors, and visual and guiding of the truck drivers. Next, under 5 minutes. Civilian aircraft presently use two types of ground-based radio navigation. They are VU or DME or non-precision approach. That is, accuracy is not good. Then there is an instrument landing system that is called category 1 precision landing. Accuracy is as good as 5 meters, but it is a difficult and costly system. Now, both these systems are not accurate and reliable for safe landing of aircraft. So once pilot gets a clear view of the runway by landing, he judges and lands the aircraft safely. So the pilot has to be guided when he lands using a good system with an accuracy of 5 meters to be guided so that he can see the runway and then land. So apart from poor accuracy, non-availability in case of, and also visibility is poor, pilot cannot make good judgment and is forced to land using his own skill. Next. So aircraft navigation is one of the applications. Even our aircrafts used in defense are going to use it. In remote sensing, we use low orbiting satellites like engine remote sensing satellite, and they take pictures of the Earth, and these imageries are taken by the satellite and sent to the Earth. The imagery is taken in a visible region is very useful for preparing maps like Google Maps. These imageries taken for satellites are usually distorted because the lens used in a satellite camera distorts the picture taken. So you have to correct the picture. NAVIC can be used for correction of this distortion of the imagery. That is, you can identify on the imagery some 4 or 5 landmarks, determine their position accurately, and knowing their positions, you can determine the distortion and correct it. In addition, a NAVIC receiver on board a remote sensing satellite can be very useful for precise position of the satellite while taking imageries. So while taking the imageries, you should know the position of the satellite also. So if you put a NAVIC receiver on the satellite, you know the position of the satellite also accurate. So this is a remote sensing application. Next. So this is just a map. So these are all possible because of the Google Map, possible because of the accurate navigation systems and corrected using the what is called ground control points. Next. Geodesy and mapping. In olden days, surveyors used geodesics and chain for conducting land surveys and mapping. It suffers from many drawbacks like bulky instruments, less accuracy, more tedious, more time consuming, and they are very costly. You see, when the British started, it was around 1780 they started survey of India, and around 1880 they completed. It took 100 years to prepare the map, which even now the Survey of India uses. But now satellite navigation receivers are small, handy, automatic, and you can use it to determine the coordinates of any place and improve the maps. Geodesy is the study of determination of size and shape of the Earth. Plate tectonics, geodetermination, satellite navigation techniques are the best in comparison to old methods for these three studies. Navigation satellites are also used in orbit determination of altimeter satellites. These altimeter satellites are used for determining what is called geo, means in Earth. But you should know the position of satellite. Navigation satellites can be used. Next.
Excuse me, Dr. Sivaraman, can we rush a bit fast? Already time is...
Just, this is the last one.
Okay.
These are location-based services is a new and emerging service that has gathered interest over the last few years. According to Wikipedia, location-based services are information and entertainment services, accessible with the mobile services to the mobile network and utilizing the ability to make use of geographical position of the mobile device. The satellite navigation system like Navit can be used to provide the geographical position. The main advantage is that mobile users don't have to manually specify zip codes or other location information to use LBS when they can roam in different locations. The best examples of LBS are Ola and Uber taxi service. There are others too. Next. The geographic information system. It is a computer-based system capturing and storing images. Next. These images, we need a coordinates. So geographic information system gives information about population and many other things, and the coordinates are also used in that. Now we have developed India. We already developed a smartphone using our ISRO Navig technology, and it is available for purchase, and that is what is shown here. It costs around 37,999, and there are models available, and they are coming into the market soon. Next. Basically, the stack technology is used. Next. Finally, I thank Mr. Kuti for inviting me to give this talk, and also all others for your participation. Thank you. Okay.
Thank you, Sivaraman sir, for a wonderful speech. Thank you, Sivaraman sir, for your wonderful talk about our indigenous geopositioning system. That's our NAVIC, and we all proud about that, and we know that how does it work, and it's also a very informative talk from your part, from a veteran scientist. And its next turn is to our panelists. I first invite the veteran scientist, Dr. Sundaramurthy, to talk about this topic. And a warm welcome, Sundaramurthy sir.
One and all, I think it is a pleasure in joining for this webinar, especially Dr. Sivaraman sir. But I didn't have much personal touch with him. But through our Retired Officers Association, we are now in contact in the WhatsApp group. In addition to that, I am seeing Dr. Navalgund sir and my Guru Rangarajan, PJ Bhatt and all is participating. Really, it's a great thing for me to be in this forum. And I don't know how I'm suitable to be one of the panelists. 3 days back, Kuti sir has called me and he was telling me, can you be a panelist? Then I told, okay sir, I think but after seeing this, I'm afraid. I don't know, because I learned whatever I know, it is because of our Gurujis. They are already sitting here. Okay, to summarize Dr. Sivaraman's presentations, he has precisely brought out the GPS from the basics, and he has covered very much in detail. In fact, what I can say, he has taken a classroom for us, how the GPS is working with kind of a detailed explanations, and he has given various parameters, then how that can be derived and how it is used to locate the positioning. Back to this, of these things, I just whatever I collected was this was basically established by Department of Defense of US in 1973. They conceived this idea. They originally used it to track the ship. That was the main thing which they have started with. Finally, okay, they started and improving it, and sometime in 1993 they have fully established this constellation of 24 satellites. That is that 6 satellites in 4 satellites in 6 plane, and they are having currently 31 satellites now in the orbit. And it was originally meant only for the military people, but later in 2000 onwards, it went to the civil people also. But when come to a having system, okay, when you are pushed to the corner, definitely we will find out something new. That is how I think Pokhran has given us to go for our indigenous efforts to make our own rocket systems. That is what our Dr. Kalam we used to tell. Similarly, during Kargil War in 1999, GPS was denying the required accuracy to be required for our defense people. So, at the time, I think Dr. Vajpayee was the PM, and he called Dr. Rangan sir, he was the chairman, because once he was narrating how this Navik has been derived. So, what we have come out after analyzing all the pros and cons, we settled for a system which is only regional specific, that is 1500 kilometers around our Indian region we were concentrating, and that we could get 3 geostationary satellites and then 2 in geosynchronous orbits, that is that inclined orbits. That is how that 7 satellite configuration have been evolved. And of course, Dr. Sivaraman sir has already explained in great detail their positions and other things. Now, after all the experimentation and the other things, yes, I am happy to see that already it is available in the mobile form. And I think in future, we will be able to replace the GPS with our own Navik system. And one small thing which I wanted to add our Dr. Sivaraman's explanation about is, it's one easy way of explaining this, our positioning system is something like this. Let us see, when you are driving in some place, your vehicle has gone bad, but you don't know where are you. Unfortunately, your mobile at the time, even if the signals are not there, but probably if you can contact somebody, let us see, you call a friend from Trivandrum. That fellow may be telling you, you are something like 1,000 kilometers away from Trivandrum. Then you know you are from Trivandrum, 1,000 kilometers radius of circle. Then you find out somebody who is in Chennai. That fellow, he says, you are 400 kilometers away from Chennai. That means then if you draw 2 circles of 1,000 kilometers and 400 kilometers, you will get that to 2 points. Then if you call another guy who is in Hyderabad, that fellow may be telling some distance, let us say it is 300 kilometers, then it will be zeroing on the point where you are. Now you can easily locate where your point is. It is applicable for a 2D kind of a configuration, whereas in the space system, you need one more. What is your altitude also? That is how Dr. Sivaraman's Shah's explanation of that 4 satellites you required minimum to have the position. But by having more number of spacecrafts, you can improve the accuracies. But it is one thing which now we are all clear. GPS can give something like 100 meters or so. whereas our Navik is getting 20 meters, the accuracy. I think we are all waiting for the day where we should replace GPS with our own navigation systems. I think I'm not going to add much. Thanks for giving me an opportunity to be in this platform with the elite people like, in fact, I'm really glad to see Dr. Rangarajan, PJ Bhatt and all. Thank you so much, Kuti Saab. You have given me an opportunity to interact with all these people. Thank you so much.
Thank you, Sundaramurthy sir. And we are optimistic that we will replace our GPS and with our own Navic. That's why along with us, we have the working scientists also stay with us. Dr. Rajat Acharya and Dr. Ashish Shukla is with us. And we expect a lot of contribution from the growth of this ISRO and SSC. And from their part, it's their turn to speak to these things. And one more thing I want to add, we use the service of panelists for the students. And after the panelist talk, micro talk, and there is a chance for students, and the students will exactly explore our panelist and the presenter. That's our practice. And first, I invite Rajat Acharya sir to speak on and put a light on the findings and sayings of Sivaraman sir and Sundaramurthy sir. Welcome, Acharya sir.
Thank you so much. Thank you, Dr. Sivaraman. You have already explained most of the aspects of the satellite navigation in the very lucid way you had always been. So thank you so much, Dr. Sivaraman. And as Dr. Murthy has already mentioned, that in our daily life, we are using this knowingly or unknowingly, we are using this methodology of finding our position in certain way, which will give us certain some easier means, easier way to find out what our position is. One point which I would like to start with is that many of us have the concept that, or have the idea that GPS was the first satellite navigation. Actually, that is not. The first satellite ever launched was Sputnik. It was in 1957, October 1957. And using the signals coming from the Sputnik and using the Doppler methodology, the positions were, some people were able to find the position. So right from that point of time, the positioning on the Earth's surface using signals from the satellite are going on. And before GPS, there were satellites like, if I remember, there were satellites like Transit, then Timation, and there was a USSR satellite that was called Sikor. These are satellites which were used for finding the position, but definitely the way of finding the position was different from that we are doing in GPS or in Navi. Now, one point that Dr. Murthy has rightly mentioned, that it is not a very difficult thing to understand how the GPS works. As Dr. Sivaraman has already lucidly described it, like we do in for the sake of our students, I'd like to mention that like we do on the graph paper, when we try to find some point, what we do, we find the distance from the x-axis, we find the distance from the y-axis. If we do that, if we find these two distances, then we can find one definite point. Now, if we extend it for 3 dimensions, and if we extend it for the where our reference lines become some reference points, then what we get is some spherical equations, what Sivaraman sir has already mentioned. So by solving those spherical equations are nothing but where you can be knowing the range from a definite point. So it gives you a sphere. It gives you a surface that is a sphere. Then if you solve, and if you know that from each of the points you are at certain distance, you form 3 or 4 such spheres, and where these spheres intersect at the common point, that is your position. That has been already mentioned by Sivaraman sir, and that is not a very difficult thing to find. But what I want to point out that prior to GPS, there are certain other means which are called the hyperbolic mean of finding the position. Like in GPS, what we do, we find the direct range from each individual satellite. But if we can do it by finding the range difference from 2 different satellites, then the kind of equation that is formed is a hyperbolic equation. The surface that is formed, instead of being a sphere, it becomes a hyperbola. So where these hyperbolic surfaces intersect gives me my position. That is another way of finding the position. So there are different means where out of this, the satellite, the GPS uses the spherical equations for finding the position. And that's very simple, as Sivaraman sir has already mentioned. Another point which I want to mention here, that many of the persons who are attending this seminar, I can find are very young, and I think they are students. So for them, I would like to say that if you continue, if you are interested in this particular subject, and if you want to continue your studies, your researches in this area, I can tell you that it's the right time, and it's very high time that you can do that, because GPS and GNSS is coming up in a very big manner. If you are doing research, then there are so many, in addition to the main research of the GPS, there are so many spin-offs, like researches in ionosphere, researches in atmosphere, and also certain applications like location-based services, as sir has mentioned. Like, for example, I have gone to certain place, and I had never been there before, and I want to know what is the weather will there the next day. So I can ask the location-based service providers that what will be the weather where my position is currently is, and that I can get. And that I can get with the help of my position, because I am telling my position, then only I am getting the response back. So location-based services is another area where researches and works are coming up in a very big manner. And what I was telling, that if you want to continue in this line, then there are so many of courses currently available online. You can find it in the internet as well. Many of the universities are currently showing interest, and they are introducing different courses in their curriculum in this respective subject. And so many industries are also coming up where you can contribute and get your make your career in your future. So there are many industries on the current date, and many startups have started, and they are coming up very good manner, and you can think of a career in this line. And for that, you have to continue reading and liking this subject, and continue reading. There are lots and lots of internet materials, and you can learn from them. And definitely we are here. If you need some assistance, some guidance, then we can also provide you. And from the perspective of SAC, I can assure you, we are working so that in recent future, as some of my earlier speakers were saying, that in recent future, we will definitely be seeing the GPS being mostly replaced by our own this NAVIC system. So with that, I conclude my current talk. And if you have any definite questions, so I can answer you later.
Thank you, Rajat sir. We are so happy to hear that something is going on to replace the GPS from our own ISRO, and that we are expecting. And we expect some more lights and information on this future of our navigation system and the development from our expert panelist, Dr. Ashish Shukla sir is there, and I invite Ashish Shukla sir to speak on this topic. Welcome, Ashish sir.
Thank you, Mr. Sajil.
Yes, sir. Thank you.
First of all, thank you for organizing this webinar on satellite navigation, which was talk was given by Dr. Sivaraman, to whom I consider my guru and mentor here. Whatever I know in satellite navigation, it's because of him only. So it was great to hear from him. Uh, I heard him after a very long time, maybe after 5-6 years. So it was a great opportunity for me as well to re-hear from him about this topic. I also thank Dr. Kutti. Dr. R.R. Navalgund is here. So he was the director under whom I started working in SAC ISRO, and he guided us a lot on these things. And there are some students also, and I'm sure they have got benefited from the lecture by Dr. Sivaraman, which was given in a very simplistic manner how we can use satellite-based navigation systems for find a location on the surface of Earth or above the Earth on a spacecraft or an aircraft. So uh, uh, I'm working in satellite navigation since last 15 years, and I've worked both in the development of Gagan and Navik, both the systems, and we have recently developed a ground-based navigation system called pseudolite-based navigation system. So these are some things students can take interest in and pursue their career. So these systems are very essential nowadays in our daily life. Uh, Whatever application you name, say scientific application, defense application, remote sensing application, mobile-based location apps, and aviation application, many whatever application you name, you can do using these satellite-based navigation systems, mainly GPS, GLONASS, Galileo is coming up, and many more systems like this QZSS is there, Navik is also our own Indian system. So we are now independent in satellite navigation. Earlier, we had dependency on other countries. So that was a great thing. And today, this system is fully developed and working beautifully. And accuracy is at par with any other system in the world. So that is a great thing. And so nowadays, we can get accuracy in meter level to millimeter level, and centimeter level accuracy is also available to us with some very advanced navigation processing algorithms and techniques like precise point positioning, we call PPP, and RTK positioning, we call real-time kinematic positioning. There we use very precise carrier range measurements, and we can even get centimeter to millimeter level accuracy. So those can cater to some specific users like survey and land records, dam deformation, plate tectonics, and then precision agriculture, and many other applications which require centimeter to millimeter level position accuracy. So now it's time to go for, as everybody has stressed upon, that we have our own NAVIC. Earlier it was GPS. but I'm stressing that this era is the era of multi-constellation and multi-frequency satellite-based navigation systems. So we are seeing a GNSS receiver which is capable of GPS, Galileo, GLONASS, NAVIC, QZSS, and everything. So, and advantage of this is that we are getting so many signals, so signal availability is more. Say some signals are obstructed, then also we have plenty of signals to process and get the accurate position. So that is, and in mobile chip also, Dr. Shivraman has stressed one Realme mobile phone is coming, and also some more companies are Qualcomm and other companies are making some chips which are coming in some mobile phones in coming time. So this is a era of different kind of developments, and students can get exposure of that. In fact, also we have started Navik Gagan utilization program, which is running successfully from last 3 years. Phase 1 is already completed, and we have involved around 30 academic institutes, including IITs and various Indian universities, including NITs. And second phase is also we are going to start. There, students can join as a junior research fellow. They can do PhD, and some people may join as faculties also and take the project and do the research work. So now this was done by with the aim to spread the awareness about satellite navigation to the entire country through the academic institutes. So I'm very hopeful that some of the students will get benefited from this webinar, and they will be excited by Shivraman sir's lecture and exposure from many other literatures and books. So I'm hopeful that they will be joining us in some way or other in future. Thank you so much.
Thank you, Ashish sir, for your wonderful talk, and it was a great motivational and inspirational one. And that's why, what's the scope of this NAVIC system and what we expect from SAC. And the main target group is our students. They are eagerly waiting there to ask some doubts. And definitely, and we hope that from your talk, we hope that we will reach in a position for the accuracy of millimeter. That's a wonderful thing, and we are respect from your part. Along with that, we need your help also, because you are presently with part of ISRO, and there will be a hand to these students when they reach to their position to help them. Okay, sir. Thank you. And again, I invite Varun to deal with the questions. That's the main utilization point of these things, these webinar. That's the main point of this webinar. And these students will have to explore these eminent scientists and to their experiences. And I invite Varun to ask questions directly. Along with him, his co-partner, that is Bharat, is also there. He can also join.
Sir, Bharat has the question from the chat box, and I think he handle the question answer session.
Okay. Then Bharat, okay.
Okay. Thank you, sir. Thank you, Arnata. Before we move into the Q&A session, let me take this opportunity to thank our speakers and panelists and everybody who has gathered here. First, thank you, Sivaraman sir. It has been a beautiful presentation. We've been able to understand about GPS, NAVIC, and all sorts of navigation systems that exist today and has existed before. Besides, I also thank Rajat Acharya sir, Ashish Shukla sir, as well as Sundaramurthy sir. This webinar today has been a little special for us, because considering the fact that throughout we have had a lot of veteran scientists from ISRO, this time we've had some working scientists as well. So I hope we'll be able to get in touch with the present circumstances as well. So let's move into the Q&A session. What I find very curious today is that for the past few weeks, like, this is the 10th webinar. For the past few weeks, Sivaraman sir has been an active participant of the webinar, and you might have noticed that he asks questions with the same spirit as students does. Now, fortunately, he has found himself on the side answering those questions. So let me invite the students to ask the question. The first question is from Febin. It is. I have to say that the questions we have had a lot of questions, and today's webinar has been really good, and it is evident from the number of questions that we have received today. So the first question, as I said, is from Febin. He has asked 4 questions already, so I would like to tell him to please ask the first question now. Febin, can you please come forward and ask your first question?
I think there is some connectivity problem with Febin. He is not seen here. Then you can ask it. And one more thing, if anybody lose this webinar or unable to attend it, don't worry. We are continuously recording it in HD form. And again with that, we are streaming it live through our YouTube channel. So it's available forever and it's recorded forever, this wonderful speech. And Febin will get it when he joins there. And Bharat can ask the question for Febin now.
Okay, sir. Is from Febin and is asked, sir, why is India trying to increase the number of satellites from 7 to 11 in the NAVIC system?
Very good question, Mr. Febin. Why India is trying to increase number of satellites from 7 to 11? You see, these 7 satellites are providing service over India. If one of the satellites fails, what will happen? There will be only 6 satellites and there will be outages. Many times you will get 4 satellites. So these 7 satellites are minimum to get 4 satellites every 24 hours. So also ISRO has a plan to expand it to a global system like GPS 24 satellites so that we can have a business like USA is making GPS business. We can have our own industry developing the receivers and selling to others. In future, the system will be NAVIC plus GPS plus GNSS plus all sorts of things. So if we have got our own 24 satellites all over the world, we can have service everywhere in the world, especially with only the lower accuracy code. The other code, which gives better accuracy, we are restricted to only to defense. Moreover, apart from the failures and other things, see, we had 2 failures. Once INSAT 1A failed, and IR INSAT 1A failed, and we had some gap. Similarly, one of our satellites didn't come out of the code, and we were not ready with another satellite immediately. So a spare satellites on board is very essential. Thank you.
Bharat, you can come with the second question of Febin.
Okay, sir. Thank you, Sivaraman, sir. The next question is from Abhiram. If you notice the chat box, we've had quite a lot of competition in asking questions between Abhiram and Febin. Both of them are really active participants of our webinar. So let me invite Abhiram to ask his questions. He's also asked a lot of questions. Now, to be specific, I would like him to ask his second question now. Abhiram, please come forward.
Okay, thank you, Bharatata. First of all, thank you, Sivaraman sir, for your talk. Sir, my doubt is here. Sir, how does the fast-moving clocks become slower than slow-moving clocks? Can you answer that question?
Abhiram, can you please speak a little louder?
Okay. Sir, my question is this. How does the fast-moving clocks become slower than slow-moving clocks?
Should I repeat? How
Okay,
does
sir.
the fast-moving clocks become slower
Okay, sir.
than slow-moving clocks?
Yes, sir. Yes.
Dr. Jets, can you answer? I think fast-moving clocks, very fast-moving clocks. Actually, whenever according to the theory of relativity, whenever a clock is moving fast, the time becomes slower. So in slow-moving vehicles, the times run faster than the fast-moving vehicles. That is the explanation given by general theory of relativity. Now you have to understand the general theory of relativity. I am not so good in that. But this is the case. If we can go as fast as velocity of light, time will stand still. I think that is the answer. Any?
Thank you, sir. Maybe he asked the doubt more like, yeah, maybe he meant the general theory of relativity. We all know that about the proposal of the, relativity that, when this height of the body increases, the time on that part is, it gets faster, right? Or was it slower near the surface of the earth? I don't exactly remember. Maybe it's like because of these effects, the time on two places, one maybe near the surface of the earth and uh, farther away from the surface of the earth, differs. So maybe that is what he actually meant. I think, Abhiram, you can continue with the next question you asked.
Okay. Sir, my another question is this. Did the satellites rotate when they are orbiting? Else, did the satellites use the fuel to control that position?
Shall I answer? See, many of the satellites, like remote sensing satellites or communication satellites, they are stabilized, 3-axis stabilized. Their antenna or the camera always looks towards the earth. So only scientific satellites orbiting, they rotate, and that is called spin stabilization. But other satellites like remote sensing satellite and communicate satellites, they are 3-axis stabilized. And if there is a disturbance in there looking towards the earth and transmitting signal to the earth, the fuel can be used to control that. And that is what is done. I hope I answered to some extent. Dr. Murthy,
Sir,
any?
Sir, did we use the
Probably
solar
Dr.
panel
Sundaram
to make that fuel for thrusters?
I think, Abraham, can you repeat the question, please?
Yes, sir.
I think your audio is not very clear.
Okay, sir.
Volume.
Now is it okay?
Yeah, please.
I will repeat.
Yeah,
Yes,
please.
sir, I will repeat. Did the satellites rotate when orbiting? That is, do our satellites rotate while they are orbiting on their
Yeah,
orbit?
actually, yeah, yes, sir. See, what is happening, if you take a communication satellite, though it is geostationary, but always the antenna is supposed to look at the point where it is supposed to be pointing. So, over the period of time, over the 24 hours, the satellite also makes one revolution about its own axis. Otherwise, that pointing of the antenna cannot be ensured. Whereas this may not be the case for our remote sensing satellites. Only when there is a imaging is going to be taken, it has to be pointed. Rest of the time, yes, it need not be. So that is how that pointing mechanism takes care of it. So some of the satellites will rotate on its own. That is mainly because of our geostationary orbit kind of a things. Whereas for remote sensing, that may not be applicable. If you look at IRNSS, I think it makes a kind of a 8. I think what we will do is, we will make the 180 rotation. It is mainly to take care of the solar radiation effects. That is the main reason we take in IRNS that that other half we will rotate.
Do you use fuel for control it?
See, generally we will not use, that is, we use the stabilizer systems, that momentum wheels we make use. Because of that, the attitude is being held, and when the speed, normally we allow the error to build up to an extent of 10% of the RPM. Once it crosses that 10 RPM, 10%, then we will offload it and then bring it to the nominal value. For that offloading the momentum, we require propellant. So it is not that on day-to-day basis this will be done. Once in a while, when the momentum picks up and then when it reaches the maximum RPM, we will offload, or if it goes down, then we'll take it up to the normal value.
Thank you.
Thank you, sir. I think Abhiram has one last question left. I think Abhiram, can you please ask the last question to me?
Okay. Bharatata, sound ready ആണോ?
Ade Abhiram, you can go on.
Sir, when we try to pass the Van Allen belt, the electronics in satellite will become bad performing.
Yes, this Van Allen belt is a belt around the Earth at a very high heights, and they are all charged particles around the Earth. Because of the Earth's magnetic field, these solar particles are trapped in that, the charged particles are trapped in that, and they form what is called a belt around the Earth, Van Allen belt. And it is highly charged. So when any spacecraft with electronics passes through that, if it is not well protected from these radiations, it is going to get damaged. So most of the spacecraft passing through the Van Allen belt is taken care so that it is not damaged due to this. And that is very essential, that we have to take care of Van Allen belt. In fact, this Van Allen belt was discovered by the first satellite launch, it is Sputnik by Russia, by accidentally. If it was not detected, probably we would not have known that there is a dangerous belt around the Earth, charged particles, which can damage our spacecraft. Very good question.
One more thing I would like.
Okay, sir.
One more thing I'd like to add to what Dr. Sivaraman has said, that there are at certain times the sun solar activity get enhanced. So there are particle radiations from the sun, energetic particles radiation from the sun, which are enhanced at certain times, and those enhanced particles with higher energy, they get trapped inside the magnetosphere of the Earth. So at certain times, the amount of energized particles in the Van Allen belt increases, and at certain other times, it reduces comparatively. So when during the time of high solar activity, when the Van Allen belt energy level gets enhanced, at that time it is very dangerous for any spacefaring vehicle to move through this region, and there is possibility of damage.
Thank you so much, sir. Thank you, Abhiram, also. There is one more question from Febin. He's not online, so I will ask that question. Can you please hold on? The question from Febin is that why do GPS receivers use MATLAB computer programming code?
I think Dr. Shukla can answer.
Yeah, actually, they don't use MATLAB programming. Generally, there are two kind of programmings in a GPS receiver. One is in hardware, so we do it by VHDL or very low code, and then there is a processor inside the this hardware, Zinc board or any hardware we use. So there we use C programming language. MATLAB is extensively used for algorithm development and simulations. So not in some software receiver people have used, but it is not very faster in nature. So generally in real-time applications only C software is used along with the hardware thing with the Verilog or VHDL code.
Thank you so much, sir. I think Sundaramurthy sir is trying to speak something. Sir?
No.
Okay, sir. So let's continue with the next question. The next question is from Adil Krishna. After seeing this, I think under this, the current circumstances, it is somewhat like a bit national issue or more like of national security and things like that. So he's asked, Sir, China's Beidou's final satellite has been launched on the 23rd of June 2020, and it's a 35 satellite constellation giving a global coverage. And China says that it's the complete alternative to all other satellite navigation systems. Can you give us some more information on this, sir? And will this replace GPS and other satellite navigation systems?
This is a good question. China, they have got 35 satellites. They use all geostationary satellites as well as orbiting satellites. So they have got more satellites, and many times they may be able to see 8 to 10 satellites at a time. So even if one satellite fails, they'll be having good coverage. But it is not correct to say that all satellite systems are alternative to GPS. For example, our Naviki is an alternative to GPS. We don't depend on GPS. It provides only regional service. So China's system is also its own system, and it can replace all other systems. They don't use GLONASS. Many of the people don't use GLONASS. So all navigation systems, because mainly they are defense oriented, they are used by their own countries only. Rajat, could you answer, or Dr. Shukla, you want to add anything? Why China claims alternative
Yes.
all other systems?
Sir, as you described, China has also developed global system, but still that system is not declared operational. So right now, only GPS and GLONASS, two systems which are global in nature, are operational systems which can provide position of any object anywhere in the globe. So, but in future, definitely this uh, uh, compass or BDO system and Galileo, uh, they are coming up. And as I had mentioned in my address just now, that this is the era of multi-constellation receivers. So in that way, we are going to get benefited from all the systems together inside a single receiver. I hope I answered, clarified your question.
Yes, sir. Thank you so much.
I would like to add, the Chinese navigation system and Russia's GLONASS system are very secretive. In fact, we don't know many of the details of these systems, even the orbital parameters and other things. So that is one of the difficulty, that why it is not worldwide use, and GPS became very popular.
Thank you
Thank
so
you.
much. Okay, sir. I would like to add something to what Ashish Shukla sir just talked about. He said that only GLONASS and GPS are presently equipped to handle or to find the location of any point or anything all over the globe. So does that mean that NAVIC is not yet operational in India?
No, first thing is NAVIC is not a global system. So I was talking about global system in particular. NAVIC is operational, very much operational, and we can get position inside the Indian mainland mass and 1500 kilometer geopolitical boundary. So that's the status as of now.
Thank you, sir. So now that the satellites are already launched, and that the next thing to do is that you need the receivers and all sorts of things in the devices that we use now. So when do we actually have to expect such a system to be common among us?
Actually, efforts are already going on. If you search on for some GNSS receiver chip or hardware, so you will get a data sheet, and in that you can see more than 400, 500 channels are there in every receiver. So they are all having the provision, already having the provision to include all the signals which are either being transmitted right now. Say China, for example, might be transmitting signals from 28, 29 satellites right now. So all those signals, Galileo is also transmitting signals from some of its satellites. Navik is transmitting signals. GPS GLONASS are already transmitting in full capacity almost. So the provision has been done already in the receiver, so that whenever satellites are getting included or constellations are getting completed, they will be automatically receiving all those signals and provide the solution or position by processing all those signals.
Thank you so much, sir. Now, I think this will be the last question that we have to address now. The question is from Vaishnav Babu. So before I ask him to tell the question, the thing is that previously we have already talked about the GPS and all sorts of location and kind of systems trying to locate things on the ground and those like air travel and all these kinds of things. But he has asked a very curious question, so I would like to invite Vaishnav to please come forward and ask that question.
Sir, hello. Can you hear me? Bharat?
Yes, Vaishnav, please continue.
Sir, my question is, can we reprogram a satellite when it is in the orbit?
I think,
Sir,
Vaishnav, I meant the next question that you have to ask. Please ask your second question.
okay. Sir, I have seen that after the launch vehicle is being located in the graph. How is it possible, sir?
Can you repeat your question?
Okay, sir. I have seen that after the launch vehicle is being located in the graph. How is it possible?
I think Dr. Murthy, Mr. Murthy can answer. Sundar Murthy.
See, actually, it's not a graph. A graph it is, they will show it is an animated thing. Do you mean to say that in the TV screen you are seeing the graph what they show as the stages when it is falling and that kind of a thing? Or is it that?
Yes, sir.
Trajectory,
Yes, sir. In the control room, trajectory path.
Yes.
In the trajectory path. Trajectory path. Trajectory path.
No, actually, what is happening? When the actual launch take place, for the first at least 1.5 minutes, you will be seeing the actual rocket, because that they are taking it from the theodolites and then whatever the cameras which they have kept, and then the balloons and all they will be capturing and then they will be showing. Once it goes out of the site, then the trajectory and other things, whatever you are seeing on the screen, are all predicted one, and whatever the tracking information coming on the real time is processed, and then that will be displayed there. Have I answered your question?
Sir, in the case of Vikram, sir, I have one more doubt, sir. In the case of Vikram, the ISRO has officially said that the Vikram has deflected its path. So how is it possible?
See, it is okay. The thing is, it is not deviated. Probably what you can say is the expected path, it has not taken in the last 1.5 minutes. That is what is been we have seen. That they were telling that error corrections could not be possible with the thrusters available on board. That could be the reason. That is what they are all. But of course, because this is beyond my purview, I can't go beyond this. Sorry.
Thank you so much,
sir.
sir.
Thank you, sir.
I think Vaishnav,
Is the question session finished?
yes, sir.
Then we have one more request from Dr. Sundarajan sir. He also want to ask some questions. Welcome, Sundarajan sir.
Okay, can I ask?
Yes, sir. Yes, sir.
Okay, this is to people who are doing NAV-IC. They said they have developed and established and all. Why it is not implemented in Indian aircrafts? Still, we get into problem in fog in Delhi and fog in Bangalore and all. If our system is already on, they should translate this to real operational mode as quickly as possible, right? Where is the bottleneck?
Actually, these systems, the new navigation systems, are undergoing testing still. And it is very difficult to convince any existing system to change over to new system. Like when I joined Geodesy, I had a great time to fight with Survey of India to switch over to satellite or using geodesy and determining coordinates rather than using the theodolites and chain. And now they are using that. And that is how we did it. And in aircraft, it is a question of safety of the passengers. And the system is existing is working, but it is costly. And the testing is going on. ICAO is trying and testing it, and it will take time to
Yeah.
adapt to the new system.
No,
And
no,
now
the
we
time
can
is
get
too long.
category
The time
1
is
to
too
system
long.
service.
It can be taken as a piggyback mode, and critical, see, a lot of maneuvers and other things are lost. We are saying NAV-IC is operational, but I don't see that in real operation when really you need Cat 3 landing and this kind of thing. That is where we need this. I understand the problem because I know how it is. So maybe the airport authority and the navigation group of
That is right.
affiliation
It is,
with
it is
ISRO
the Airport
should,
Authority of India who has to convince. We have to implement.
yeah,
See, ISRO
yeah,
has,
yeah.
in fact, Airport Authority of India approached ISRO and helped them. And myself, Dr. Kibe, Dr. Surendra Pal,
No,
all
the
these
point
guys
I'm
together,
saying,
and that
that's
is
all
how we
fine.
evolved.
ISRO
Now,
should
the
not be
operational
required
agency to do it.
for that.
Like our remote sensing activities also. The operational agency,
No,
some are using it.
No,
Communications
ISRO
also is
should
the
not
same.
be quiet, and at least Indian flag carrying aircraft they can be implemented. They
Correct.
should see that.
That's
That's
correct.
all my point.
Sir,
Correct.
can I add something?
Yeah,
Yes,
sure, please,
Yes,
please.
sir.
Sir.
Yes, sir. Ashish, sir, you can, sir.
Yeah, actually, what sir is talking about, Gagan system was meant for automatic landing of aircraft in India. So, as Shivraman sir has explained, it's a big system and many segments are there and a lot of testing was done. Now system is actually ready. However, what information I have from Airports Authority of India that problem is there from the uh, uh, operators which operate the aircrafts, operator companies. So some uh, augmentation or modification or Gagan enabled receivers, you can say, had to be put on the aircrafts. So no aircraft carrier was willing to land their aircrafts for these modifications and then for further testing because they will be used for safety of life purpose. So that was one big bottleneck which sir has pointed out. So as per our understanding, because of this bottleneck, that aviation industry is not willing right now to deplane their aircrafts for the Gagan enabled receivers installing in aircrafts. So that issue is being resolved at the ministry level, and probably we will hear some good news about that in near future.
Yeah,
Okay,
I
okay,
understand.
okay,
I
okay,
understand.
Dr. Sundarajan. Dr.
Yeah.
Sundarajan, thank you very much for coming and be with us.
No. That is okay. I agree with whatever you are saying, but only my point is ISRO should work with the aircraft operator in a joint testing program and build confidence into them that this is reliable
We
and
are
can be
working with
used.
the Airport Authority of India.
Yeah.
We
As
are
Dr.
pursuing
Shukla,
Not the
as
airport.
Dr.
I'm saying
as,
aircraft
as,
people. Yeah.
as Dr. Shukla has said, the matter has been referred to the higher levels, in the ministry levels. Let us hope that they will come out quickly with a resolution. Let's move ahead. Thank you.
Thank you, Kuti sir.
Bharat, go ahead, Bharat.
Oh, thank you, good sir. Thank you so much. Thank you so much, panelists. Thank you so much, Shivaraman sir. Thank you, Sundar Rajan sir. We've had a very live Q&A session, pretty much similar to the previous session where Shivaraman sir had come up with asking with a question. This time we've ended with Shivaraman sir with Sundar Rajan sir asking a question. So it's getting better with each webinars. Thank you so much, everybody for participating well. Thank you for answering the queries. Thank you for clearing all the doubts. So the Q&A session is hence finished. I would like to hand over the duties to our very own Shajil sir. Shajil sir,
Okay.
please.
Thank you.
Shajil Mash, can I have 2 minutes? Can I
Yes,
have
sir.
2 minutes?
I just invite you for something. That's why, sir. one second, sir. I want to say, just intended to invite you, sir. Then it's a 10th webinar we finish here, and in the 5 year back, the middleman of India and the former president passed away on this on 27th of July. And the US Space Club is also decided to some more programs. And we have our chief patron and mentor of our club, E.K. Kutisar. And he established this club at Calicut. Now it's flourished all over India. And we can say the only active space club in India also, we can say that we all sit together in a family of your space club, and we have to develop the young scientists from in Kerala and maybe from all part of India. That's a larger community we expect. And under the guidance of our guru and veteran E.K. Kutisar, I invite Kutisar to say something on the future plan, especially on the 27th day, the Kalam Day also. And I invite Kutisar to speak on that.
Thank you, Shajil. I just want to say few things. One is what Shajil wanted me to say about the Space Club. Before that, now Dr. N. Sundararajan is coming, and we are seeing him talking after a long time. I think he is not in our shore. He is in Singapore, if I understand correctly. And very warm welcome, Dr. Sundararajan, for being with us today. And Dr. Sundararajan has already agreed to give a webinar on some other occasion. He is a launch vehicle expert of ISRO, and has been in teaching in the Singapore University as a very senior professor for quite long. So thank you very much, Sundararajan, for being with us. Now, this today is a very important day. This is the 10th webinar of ours, as Shajil Mash has already said. 23rd May we began, and this is the 10th one. And today we have very senior people like Dr. Naval Gund, Rangarajan, PJ Bhatt, I don't know, Ganesh Raj is here, and very people like that. Of course, what is most important to us is the speaker and the students. And the speaker, Dr. M.R. Sivaraman, has done a very good job, and Sundara Murthy has been with us, and he will be coming to give a webinar later. And Dr. Acharya and Ashish Shukla, they have done a fantastic job. Now, it is a very wonderful day for me, a very special day for me, because the year in which I exited ISRO, Dr. Shukla joined ISRO, SAC. Now, everybody who is to join ISRO, particularly scientists, I used to have the privilege of meeting them, inducting them in some way, and all that thing. And I have missed it for quite long, for 15 years. And today I am meeting a person who has joined immediately after my exiting the organization. And this young blood, now Shukla as well as Acharya, they are going to be a kind of a motivation for our students. We hope that they will be available as and when we find there is a need for them. Now, our further programs, as Shajil has said, we have a Kalam Memorial Talk on 27th. It is by Dr. Mr. P.N. Subramaniam, a long-time associate of Dr. Abdul Kalam in Trivandrum. He has been there from the very beginning in composite materials group. At that time, it was called Fiber Reinforced Plastic Center and all that. So he will be talking on Dr. Abdul Kalam, his close associate in those days. And this program is on 27th at 3. P.N. Subramaniam has a trust in the name of Dr. Abdul Kalam. They are promoting lot of activities in the memory and in the spirit of Dr. Kalam. Now we have next Saturday, that is 1st August, our Dr. S. Rangarajan, who is already here present with us. He will be talking to us on 1st August, and the topic he will be talking is most probably space and education. Our students will be quite excited on that, and our own friend and our guide and our guru, Papan, P. Patmanabhan, has agreed to be one of the panelists, and we will find another panelist, if possible, from IIST. I am trying to get one. So in that case, we will have on 1st August, Dr. S. Rangarajan talking to us with 2 panelists. So this is what I wanted to say in this short time, and this experience is something great for us. The students, something like 50 students are there today with us as we began, and they are finding lot of directions, new directions and new targets for their future